call, in a power system so far, we have not considered the transformer, right? Because if I consider transformer, then things will become lengthy. That's why that every power system, right? Suppose you have a generator, then you have a transformer, right? At the power plant, then voltage will be step up, right? Then line will go. Suppose, for example, this side 11 kV side and this is 220 kV side of a generating plant, for example, right? So this line will be 220 kV line, right? Then again it will go to substation. There we represent by bus bar. Then again suppose voltage will be step down. Say this is 220 kV line. This is 220. This will be 132 kV. Right. Again this line will go. Again from here it will go somewhere. It may have so many generators, so many lines, right? So voltage will be slowly and slowly step down. Finally it will come to 11 kV. Right. So everywhere transformer is there. Right. Here or here at the generating plant or in the line, transformer will be there, right? So the transformer, when we are studying load flow studies, the transformer we have not considered, because if I consider, then here you have to also create another bus bar, right? The things will become, clumsy. Classroom exercise, another thing you cannot do. But every transformer has a tap setting, right? For example, suppose this is a transformer. Suppose this is your primary side, and this is your say secondary side. I'm at Q, right? And this side turns ratio, suppose NP, and this side turns rather I can put it here. This side is NP, and this side is NQ. Primary side is your NP. I'm not telling high voltage or low voltage. And secondary side is NQ, right? If this is so, then this one also can be represented like this. It is 1 is to A, right? Where A is equal to NQ by NP, right? This is NQ by NP, so 1 is to A, right? This is how we represent a transformer as a tap setting. If A is 1, for example, that is NP is equal to NQ, right? Your NP is equal to NQ. Generally, that every transformer has tap. It has a step. It depends on this. It has a step 1.25%, right? For each step, and voltage may vary from 0.9 to 1.10 per unit. And each step is 1.25. You can step up or you can step down, right? So somebody's microphone is switched up. Microphone, you put it off. Somebody's please put it off. Noise is coming, right? So question is that in a step of 1.25%, you can increase the voltage, or suppose voltage is low, so you can change the tap setting. And online tap changer is also there, right? Offline is also there, right? And accordingly, you can change your what you call tap setting such that voltage can be raised. So every transformer has tap, right? So that's why your what you call that's why here this is just try to understand. Things are very simple. In machine you have studied, this is a transformer, this is a primary side, this is a secondary side, right? And what we have done is this transformer has your resistance and reactance, right? Instead of resistance and reactance, that is R plus jx, we represent it by admittance. Suppose this YPQ actually, that is P to Q, it is actually transformer admittance, and it is taken out, and this bus bar is a fictitious bus bar. In reality, it is not there, right? Just for our your clarification, this bus is called T bus, as if this transformer has no impedance or no admittance. This actually this transformer admittance is taken out instead of impedance, say, because in load flow studies we represent admittance, right? And we represent a fictitious bus that is called T, right? In reality, it is not there. But and this ratio I told you, if this side is NP turn, this side is NQ turn, then this should be your NQ by NP. That is 1 is to A, right? Another thing is the way we have taken this side current being injected at P, this side current is injected at Q. It doesn't matter. So the way you take the direction doesn't matter. Final result will remain the same. So this side turns ratio is NP. So NP into IP plus NQ into IQ is equal to 0, because MMF from this side must be equal to this side, right? So that concept we will use. So because of due to this, therefore Vt is equal to, you can write this Vt is equal to, it will be Vq by A. This is 1 is to A, and IP is equal to, you can write minus AIQ, because your NP IP plus NQ is equal to 0, right? And A is equal to NQ by your NQ by NP. So from this, you will get uh, that IP is equal to minus of A into IQ, right? This is the thing. Now the current IP can be given as, this is the current, this is the admittance. So current can be given as IP is equal to YPQ into VP minus VT, that is VP minus this VT, right? And therefore IP is equal to YPQ VP, right, minus your what you call that your Vt is equal to Vq upon A. You substitute here Vt is equal to Vq upon A, right? So this is, you got equation for IP. Now from this equation, equation 76, IQ is equal to minus IP upon A, right? Therefore from 70, that means this IQ, whatever your this thing minus IP by A, this IP is equal to this much. So you substitute here. So IQ will be minus A into this one. What is your IP, right? Therefore, IP can be written is like this. Now, this equation 78 and 78, that means this equation and this equation 80 can be written in the matrix form, right? You put in this way, this is the matrix form. Now, we have to represent pi representation, right? So now YPP is YPQ is there. YPQ you can write, look how we are doing it. YPQ write, YPQ will be there, you add YPQ by A, subtract YPQ by A, right? That means YPP should be equal to YPQ upon A plus A minus 1 upon A YPQ, right? Similarly, YQQ, that is your YPQ upon A square, right? So what you can do is, you add YPQ by A and subtract YPQ by A, right? That is YQQ will be YPQ upon A square is equal to YPQ upon A plus 1 minus A upon A square, YPQ. Now, if it is YPP and YQQ are known, right, and therefore you can represent the transformer like this. This is your non-tap side, this is your tap side, right, and this is your P, this is your Q, this is your shunt branch, right? Like YPP will be YPQ upon A plus your what you call A minus 1 upon A YPQ, this is shunt branch, and YQQ will be same as YPQ upon A plus 1 minus A upon A square YPQ. In power system studies, we represent the transformer in a pi model, right? If A is equal to 1, that is nominal trans ratio, if A is equal to 1, then shunt branch doesn't exist, right? In that case, it is simply YPQ, but if A not is equal to 1, then the shunt branch exists, right? Therefore, in a power system studies, that if two shunt branch will be there, for example, then if this transformer is there, no, that means here you have one, here you will have one, here you will have one shunt branch, right? You make ground and this side, this bus is connected here. So another shunt branch for transformer will be here, right? So this is one shunt branch. Now you will take primary, secondary, this another elements are there. In addition to that charging admittance, whatever you are adding shunt branch, this thing also has to be added. That's why for load flow studies, when you are doing in the class, we are not teaching that because things will become complex. Similarly here also, suppose you have a transformer. So here also you have a shunt branch, right? I can put it here, transformer shunt branch, and another I can put it in this bus. This whatever charging admittance, everything is there. The shunt charging admittance. Along with that, this one will be added. Along with that, this one will be added. That's why I didn't consider that. Generally, when a teacher is teaching load flow studies in class, he or she does not consider this, right? Because things will become clumsy. I mean, it will be complicated. But generally, this transformer we represent like this a pi model, right? So this is a straightforward and very simple thing. Only this thing, right? And this is up to this. It is your syllabus, and only thing is that you will solve, right? Only two examples I'll give. I'll give simple one as an assignment, that is 7.5 and 7.6, right? These two. So I'll ask you to submit later 7.6 and 5 or 7. Just last, I think these two. 7.5 and 7.6, right? So 7.5. 7.5 and 7. These two are the assignment that you will do, right? Similarly, for transmission system, I think I forgot to give you assignment. Nowadays, this time I am giving very just one. I am giving very less number of assignment compared to the last year. If you have you can ask your seniors, they can tell you. Last time I gave several numericals, right? Just hold on. Here also, what you will do, maybe signals and network course you have studied, you will do this 11, and 12, these two problems. Only 11 and 12, these two you will do. 11 is theory, right, and 12, right. This is from signals and network course, ABCD parameter, you have studied, but anyway, your power system, you will do when there is a series, when there is a parallel, what will be the ABCD parameter two line. It is 6.11 and 6.12. Right. This we will do from chapter 3. 6.11, 6.12. Right. This is an exercise. So next is and let me tell you one thing, that do whatever all problems are here, you try to do it. And I have taken the question several times, things are okay, right? But question is that do not ask any question to yes, all the 40 years are very good students. Let me tell you, those 4 students, those who are conducting this exam, these are very good students. If you ask them any question, they will not tell you anything, right? So question is that they are very small, right? And your what call, you will think an answer, particularly the first question. And second question is very easy, but hand should look like machine, right? And read carefully, and accordingly you will do it, right? First test was easy. Second test will be test time for all of you, right? And I appreciate if anybody can make full answer, but particularly the way I have made it. Book will not get, but read carefully. Don't ask any question. Right now, I just give a brief introduction of symmetrical fault, and then we will close, and Wednesday will this thing, right? So now symmetrical fault. Actually, symmetrical fault means there is a three-phase fault. That means three-phase fault. I mean, three lines. Three phases. That is three lines. They are bunched together all of a sudden, right? It can happen, but very rare. Sometimes a tree touching the three phases. This may happen. Sometimes cutting the cables when they are digging something. Suppose underground cable was there. So all of a sudden, this may also happen. But probability of happening of three-phase fault is very rare, right? But its severity is more, right? So this is a severe fault. That means that current during this type of fault, actually huge fault current flows, right? So and it's spread across your what you call your line very quickly, right? And another thing is that for fault studies, that fault current is so high that we will not consider the load current during fault, because load current is so small that we can ignore as compared to the fault current, right? So the magnitude of the fault current depends on the internal impedance of the synchronous generator and the impedance of the intervening circuit, right? So actually for the purpose of fault study, generator behavior can be divided into 3 different periods. The subtransient period lasting only for the first few cycles, then your transient period covering a relatively longer time, and then steady state period, right? So subtransient reactance, transient reactance, and steady state reactance, all these things may be necessary during these fall studies. Little bit you have studied in your fourth semester, perhaps, that electrical machine course, right? Another important point is that circuit breaker rated MVA. Because of this fault current, that an engineer or a designer, he will find out what is the rated capacity of what should be the rated capacity of the circuit breaker. After making running all software or all fault studies, he or she will see what will be your what you call that your fault current, and accordingly that MVA rating of the circuit breaker will be your what you call selected, right? Because if any fault happens, circuit breaker actually, you know, from the meaning of circuit breaker means it trips the circuit, it isolates the circuit, right? So anyway, circuit breaker will not be taught in this course, right? But whenever we are doing fault studies, simple assumption initially, this assumption, after that you will find this assumption I am making it, so there will be no problem. For first thing is that EMF of all generators you should take 1 angle 0 per unit. This is a first assumption, right? This will be done, that will make the analysis easy. This assumption actually simplifies the problem, and it means that the voltage itself is nominal value and the system is operating at no load at that time of fault, right? This will assume because fault current is very less, sorry, your load current is very less as compared to the fault current. So this assumption is sufficiently okay, right? So since all EMFs are equal in phase and all generators can be replaced by a single generator, right? So this also, when we will solve this, since all EMFs are equal and in phase and all the generators can be replaced by a single generator because of this assumption, because all generator EMF will be 1 angle 0. Charging capacitance of the transmission line will be ignored. No charging capacitance will be considered. And shunt element in transformer model are neglected. That is your pi model just now I showed you. Those shunt element will be neglected. So this actually makes the things very simple. For example, just one example I am giving. First one, look, no, not much study here is required. After that, next 2 3 chapters, some simple mathematics is there. For example, a synchronous generator, you will understand very easily. A synchronous generator and a synchronous motor is rated 20 MVA 12.66 kV. Having 15% shaft transient reactance, it lasts only for few cycles, right? And connected through transformer and the line as shown in figure. I'll come to that. The transformer are rated 20 MVA and 12.66 upon 66 kV. And 66 upon 12.66 kV with leakage reactance of 10% each, right? That is that is X is equal to, for those transformer is 0.1, right? The line has a reactance 8%, that is 0.08 per unit on a base of 20 MVA 66 kV. The motor is drawing 10 megawatt at 0.8 leading power factor, not lagging, leading power factor, and a terminal voltage 11 kV. Now, when a symmetrical three-phase fault occurs at the motor terminals, determine the generator and the motor currents. Also determine the fault current. So this is the generator. This is transformer T1, transformer T2. Reactance is given. This is motor, and this is another terminal. So fault has occurred. Three-phase fault occurred at the motor terminal. Right? Fault has occurred here. Now all reactances are given on a base of 20 MVA. If it is not, you have to convert it to a common base, right? But in this case, it is given on 20 MVA at appropriate voltage. Therefore, pre-fault voltage will be 11 by 12.66 because the terminal voltage was 11 kV. But here you look that each one rated as 20 MVA and 12.66, right? Therefore, that V0, that is the pre-fault voltage, will be 11 upon 12.66 angle 0. This is the voltage. The load was 10 megawatt and 0.8 power factor leading. So 20 MVA base, so 10 by 20, 0.5 per unit. So everything is per unit. So VI cos phi is equal to 0.5, right? It is leading power factor. So current was leading. So angle is 36.87 degree, 0.8 leading power factor. Therefore, I0 is equal to this much, right? That is your pre-fault current. So this is a sub-transient case. So this is EG double dash, EM double dash. This is your transformer T1 and transformer T2 J.1, right? That is the per unit reactance, and this is the line per unit reactance, right? This is J motors per unit reactance, right? And this is your V0. Under normal condition, now fault has three-phase fault occur means it is a pure short circuit from here to here, right? Total short circuit. The current will go through from this and current will go through from this, right? Because from generator, current will directly go to the fault, and from motor, current will directly go to the fault. That means fault current will be IM double dash and plus IG double dash, right? So from that you can easily make out that what will be your IG double dash, because it is pure short circuit. So no question of existence of V0, it will be 0, right? Therefore, your what you call voltage by, it is voltage behind sub-transient reactance from your figure 8.2. This figure, you just apply your KVL. So Eg double dash will be your what you call this one plus this one plus this one, all you add into current I0 you know plus your V0, right? Therefore Eg double dash will be this much. Similarly Em double dash you can calculate, that is before fault. This is before fault, and after fault this voltage is known, right? You have got this Eg double dash voltage, but this voltage is now, this is short circuit. So Eg, therefore Ig double dash will be after fault, it will be Eg double dash divided by J in bracket 0.28 plus 0.15, right? So this will be your current during fault from the generator side. Similarly from motor side, Em double dash upon J 0.15. This is 0.15 and this is Em double dash. Therefore Im double dash will be your this current, right? And therefore total current will be this much, right? And now current base current now for root 3 VI cos phi, right? But in this case it is no cos phi because it is 20 MVA base. So root 3 into your what you call V 12.66. So I base current will be this much. Now all this per unit current you multiply by this one, you will get this amount of fault current in ampere. So just for a single example, from this you can find out that your what you call that fault current is very high for your what you call for three-phase fault, right? So this is one thing. Other thing I will see in the your what you call in the next class on Thursday. But this chapter I may take another one example maximum. Nothing is there, and after that again we will move to something else, right? And after that whatever is there after the load flow studies, computationally it may not be that high, but things will be simple and easier after this, right? So Thursday again I'll come for this thing, but my suggestion is that you try to you try to do well, right? You try to do well in the exam, and this time think and answer. 1.5 hour time we will get. Only two questions are given. And do correctly. This is my suggestion. Particularly the problem from the load flow studies. Do correctly. Only two questions. One question will carry 12 marks. Another question will carry 8 marks. Right? 8-mark question is easy, very easy. But 12-mark question, you do it. And I'll appreciate that. If anybody can do top to bottom correctly, I'll really appreciate that student, right? Very simple it is, but you try to do it. I know it is online, I know everything, but you try to do it. Last time also I said something, I found 1 or 2 tests, they totally, this thing, I mean, half of the student was not in this thing, could not complete it or this thing. So this is the thing, but if you need 5-10 minutes more, I'll tell my teaching assistant to give you 5-10 minutes more. And every page you please write your name and roll number, right? And you try to do well, right? So today up to this and prepare well, wholeheartedly you prepare. Otherwise you will not get good grade. This is a testing time for this state. Why I am telling it? After receiving the question only you will know. Right, something I have made it. So just try to do it, but read carefully. I mean, what I want to mean that this load flow things, starting from the beginning, you will read Gauss-Seidel, you will need Newton-Raphson, all these things starting from the beginning you will read, right? And all these things you will read carefully. Gauss-Seidel, Newton-Raphson, everything, right? Everything you will read carefully, right? And calculation. When will be, because it is a lot of it is complex number, so I have tried my best to give it in such a fashion such that computation will be minimum. Whatever example is given here, compared to and whatever exam I have given it, that computation may be less, right? In my opinion, it will be less, because from my side also I have made little bit of exercise. It will be much less, but you should this thing. But before this thing, I'll ask you just one question. I also told you before, load flow studies, what is flat voltage start? Just tell me, so what is flat voltage start? Suppose when all data are given, slag bus is given. Then your what you call slag bus is given. Then all load data are given, right? Your admittances of the lines or y matrix is given. Everything is given. What is flat voltage start? If anybody can tell.
We consider the angle to be 0.
No, initially, suppose slack bus voltage in the load cluster is generally assume all buses are PQ buses. Let me clarify one thing. I should not tell, but still I tell. I didn't give you any PV buses. PV buses will take more time in the classroom. So only ultimate load flow problem I'm given PQ bus. Slack bus voltage is given. Then your Y matrix, right? Or if it is given also, you can easily compute. And all load data are known. And if anywhere generated data are there load, that is also known. Everything is known. So how will suppose you have, for example, a 3-bus problem. Slack bus voltage is given. How do you stay? What will be the initial values of R? Suppose slack bus voltage is 1 angle 0. What will be the initial voltage of we will take bus 2 and bus 3?
Same.
Same. That is called flat voltage start. That means its beginning, all the things should be same, right? And then after this, in the question paper, it is written that assume flat voltage start. That I have written. After that, I will not tell anything, right? So try to do. I know some of you will really do well. Some of you really do well, but I have found in the past test, I have seen everything. Your other things, somebody is sending this, some say another. I mean Thursday, not next week. I'll give you another special assignment. Some of them have sent mails. Even finally, a student also design course. So far, I have also given them something not yet checked. I understand your thing also all the time online. You also think our thing also. I have a lot of other online activities, right? Apart from first year lab online, then tutorial class is there, then final year design, then your third year course, right? Then I have perhaps I have 1 dozen PhD student. I think 12 PhD students are there. 7 of them are in the campus at present, right? So so all the time things are going on, right? But anyway, so I'll reply to all of you. First I have to reply to final year student, and but all of them. Those are another assignment. But definitely you will get all the reply by 31st March or before that. If anybody didn't get any reply from me after sending that, you please do your what you call write to me. Right, you write to me whether I have missed it or not. Right. So you will try to do well, because in past test I have found, I'll not tell, there are 4 batches. Some cases it is not good. One batch it is not at all good, right? 4 group I have made, in one group rather, one group it was not at all good, right? And some other group, many of you have got 20 out of 20s. I don't need to mention the name, but many of you got, but most of them have got 16, 17 like this due to various reasons, right? But in one particular group I have found except 2 or 3, performance was not that good, right? That group I think minimum was 8 or 9, something like this, right? So in any way, so you try well. I didn't try to other things and other thing. And if you have any question, you can ask me. Otherwise, today I'll leave you. Thursday again, it will be continuous class. Tell me anything if you have anything. Otherwise, I have to tell you thank you. First, you tell me. I'm stop presenting now. Now tell me if you have anything. Otherwise, I'll have this thing. Then okay, then no question. So TAs will already, one T has sent Google Meet link. I think Ganesh has sent to that group. Others also will send. Don't worry. And your Wednesday morning, I'll enter into each group if you have any doubt or anything. And I'll be joining 10 minutes late. First, you read the questions and other thing. I'll join around 8:10 or 8:15, right? And just try to do this, right? So. Thank you very much then today. Thank you very much. Try well. Thank you. I'm taking leave now then from you.